a few things from the previous one, but I'm going to be very quick because there are just 3 slides that I think I should mention, because my goal here, it's more, some of you are starting to do research on this topic, and I know there are some concepts that nobody tell you, that you see written. Sometimes you can deduce it, but it's also good to formalize things, you know, and also to know what to expect and what to look for, like when you were trying to analyze the data. There are a few things that, out of all that, whether you're doing cosmic rays, once again, neutrinos, gamma rays, or whatever, there are a few observables that are common to all these messengers. Usually, we talk a lot about the spectrum. People use the words spectrum, flux, intensity, and other things interchangeably, even though they are not the same. So yeah, we have the spectrum, we have the composition, and we have anisotropies, or arrival directions. These are, in general, the 3 main observables astrophysically relevant for everything that we are going to do. If you are a particle physicist, you are probably also interested in like proton-air cross-section, for example. Then you are, of course, going to need the number of muons, which is another observable that we derived somewhere here, right? So it all depends on what you're doing, but of astrophysical relevance are these 3 observables. I said that people use a few words interchangeably. So these words, like spectrum, what I'm going to call spectrum, it's like flux, intensity. I'm defining them. I don't know these definitions, okay? I apologize if they are not the conventional definitions, but this is the way I try to define things, just to make things clear. So people talk about the spectrum. What's the spectrum? Well, let's leave the spectrum aside for now. Let's take a look at the flux. So the flux is the number of particles arriving per unit area per unit time. So you put your detector somewhere, you point in a given direction of the sky, you count in a given unit of time how many particles arrive there. We also have something that I called here spectral flux. Once again, no idea if these names exist, okay? I made them up. So whenever I put spectral, it's something that it's the derivative with respect to the energy of the quantity, like the flux. So the flux is this. The derivative of the flux with respect to the energy is the spectral flux. That's the way I'm trying to organize it. I use this sometimes when I give lectures just to make things clear, because people do mix all these definitions, and sometimes this can lead to mistakes. If you are doing like gamma rays or things that are very short-lived, usually not cosmic rays. A very important concept is the concept of fluence, which is just the time integral of the flux. This is a capital phi, just to make it different. There is also something that I called here, once again, no idea if this name exists, directional flux. Why directional? Because this depends on the solid angle element, so it's the flux, considering a given solid angle element. And there is this thing that I call the intensity, which is everything together. This is not correct, I think. No, this is correct. This is phi. Okay, yeah, this is D4N. Yeah, so this is what I'm calling intensity. So the intensity is everything arriving in a given area, in a given unit time, and per energy, okay? It could also be called spectral intensity, following this naming, no? Go ahead, yeah. Following these names that I'm trying to give, but yeah, I don't think it matters that much. What matters is that you understand what you're doing. The main observable that matters here is the spectrum, which I did not define because, well, every time I'm going to use a different definition. Sometimes you multiply the intensity by energy squared, and I call that spectrum. Sometimes I don't. So spectrum would be intensity. So it depends on the context. So it's very useful just to take a look at the units on the plots when you're doing that, okay? Naming aside, the other observable that's important, it's the composition. So we have things like the depth of the shower maximum, the muon number that we derived here. And the question is, how do we infer the composition? We discussed this at length now. We usually use these X-max distributions. But there is one thing. These X-max distributions that we just talked about the whole morning, they rely on hadronic interaction models. So the hadronic interaction models, they tell us how the particles interact in the atmosphere. And how are they built? They are built based on extrapolations from experimental data, like LHC, for example. So you take data from the LHC, you build a model like this EPOS, QGIS-JET. I'm mentioning the names, it's not relevant, so that you know when you see this, if you ever encounter these names, that they are hadronic interaction models, and they are the ones that you should pay attention to when considering the uncertainties, okay? But there is one thing. The LHC does not go to the energies that we are talking about here. If we are talking about ultra-high energy cosmic rays at 10 to the 20 electron volts, the LHC, it's like 10,000, it's 4 or 5 orders of magnitude below in energy. So what is usually done is they take the accelerated data when it's available, and then they extrapolate to high energies, and that's the model. Yeah, usually people refer also to these words. Yeah, now I'm just mentioning a bunch of words that you might see in your life that when I was a student, nobody explained to me, and now I'm trying to put them together, so I think it's useful. Like this concept also of forward physics is because people doing accelerated data, they are always saying, okay, we use accelerated data to build hadronic interaction models to infer the composition of cosmic rays, right? And then they say, okay, but this is an extrapolation of LHC data. We need to improve the hadronic interaction model. We cannot do that with the LHC. We need like a forward physics facility dedicated to that. Forward physics facilities, forward because these things are high energy, so all the collisions, they happen more or less in the forward direction along the line. Yeah, and so they use this data of LHCF, F here it's for forward, Totem, Castor. They all inform us on particle physics in the forward direction, and all of this comes together to build hadronic interaction models, okay? So the X-max for hadronic interactions, it's a bit tricky. There are quite a few uncertainties. This toy model, it's good. As I mentioned here, this type of behavior qualitatively still holds, but things are not exactly like that. It's not as simple, okay? But yeah, so I'm mentioning here the main observables. Spectrum, so composition. So when we measure cosmic rays, we want to know how are they distributed in energy. I want to know what they are. What's this cosmic ray? If it's really a cosmic ray, what's the composition? And the arrival directions, the anisotropies, right? So typically, when we see arrival directions or anisotropies, the thing that it's done is some type of harmonic analysis. What's a harmonic analysis? Well, we are here, Earth is around us, just a decomposition into spherical harmonics of the signal in the sky. The simplest thing that we can do is to consider, usually, we take a distribution on a sphere, and we decompose the signal on a spherical harmonic basis. This is what a harmonic analysis is. We have all done in some undergrad course some type of harmonic analysis. There are like the spherical harmonics and so on. Yeah, we do kind of the same thing here. We just decompose on a spherical basis. And the obvious thing to do is we take the sphere and we count the number of things coming. That's a monopole. But then that's too simple, right? If you're just counting the number of things everywhere, we make no distinction. Sure, that's good as a first study, but that's not very informative. Then what's informative is the dipole. So what you do? Okay, you are not going to use the monopole at this stage, right? So you take the sphere, you cut it in half. That's a dipole. That's the simplest thing you can do. As a first analysis, that's great. And then you have like quadrupole, you have higher order multiples. That's what a harmonic analysis means. And the small scales. So essentially, the order here, so dipole, so the dipole, you cut the sphere in half. The quadrupole, you cut it again, and you keep cutting. So you keep coming down to the small scales. Small scales and isotropies, they are actually the ones that would, in principle, point to sources, right? For example, she asked here earlier in the previous lecture about angular resolution. So yeah, small scale and isotropies, they are related to that. Yeah, but they are not necessarily informative. It depends a lot on the energy range. So we have magnetic deflections, for example, of the cosmic rays. Tomorrow is going to be all about that. We have composition uncertainties that affect a bit, and so on, the measurements. Okay, so this is what I had for the previous part. Now I'm going to the part, to this lecture, actually, starting 20 minutes late. Okay, so what I'm going to do in this lecture now, so before I move on, are there questions about everything before, like things that we can quickly answer before moving on? No? I do hope that you all got an idea of, not the calculations, but just the main ingredients that go into understanding air showers and compositions and these observables that we just mentioned, because that's what we actually do in the end. So, cosmic messengers, we've seen this plot before. And what we are going to see in this lecture, you're going to see how to produce energetic particles. We're going to talk a bit about cosmic accelerators and about acceleration mechanisms and possible sources of cosmic rays, generally speaking. Low energy, high energy, everything, okay? Well, always high energy, but yeah, low energy compared to ultra high energies. So everything above 1 PV, more or less, I'm trying to cover. So cosmic accelerators. I don't remember what I had here. Yeah. So I like to start with something here like a spectral radiance type of thing. It doesn't matter. This is just how much things are emitted as a function of the energy. When we have a thermal distribution of particles, we can think that there is a curve like that. The exact shape, right now, it doesn't really matter. And it depends a bit on the temperature, like high temperature, right? T1 larger than T2, so it emits more. And we are talking here about very high energy stuff. So the first question that we should ask is it reasonable to talk about thermal high energy particles, thermal cosmic rays? Because, well, we always talk about interaction process, but is it reasonable? So can we get particles at the tail of these distributions? How to get the high energy particles? So very reasonable thing, there is this Maxwellian type distribution of velocities. We can imagine that. And we can see, okay, if I just integrate these, I can try to infer the probability of having a particle with a given energy, and so on. That's what we do. We've done that in statistical mechanics, and so on. It's not difficult to do. If you do this exercise, well, I've never done it. I just assume that this is the result you're going to get. Okay, maybe I'm wrong here. But I bet that we are not going to get a lot of particles at very high energies. If you decide to do it, please let me know, and I do hope that I'm right, because I never did it. And then, so people in the 40s, in the 50s, they were speculating about the sources. That's why I told you the history before. The sources of these energetic particles. Look at this paper from 1950. Remember, once again, air showers were discovered in 1938, although there were some hints of them before. And people were talking about, okay, which type, if these cosmic rays, they are astrophysical, they are extraterrestrial, which type of astrophysical objects can actually emit these energetic particles? This argument here, yeah, it's not going to work. I suppose they did this calculation, even though I didn't, and they probably have seen that here we don't get many particles, very energetic particles, using a Maxwellian distribution. There is this paper by Alfven and Herlofsson from 1950, in which they are actually discussing how stars, some type of star, can produce cosmic radiation. This cosmic radiation that we detect here. So this is one of the early studies trying to do astrophysics with cosmic rays, because so far it has been only particle physics, atmosphere. Now we are going outside. We are going to see, okay, these particles, they arrive here. And the next question is, where do they come from? What can we learn from them? And especially how they are produced. Okay, so what they did, I think they considered that this type of thermal distribution doesn't work, so they said, okay, there should be some type of non-thermal acceleration of particles. And now, what we are going to see now, it's mechanisms for non-thermal particle acceleration. There are two classes, broad classes of mechanisms that we could come up with to explain how high-energy particles are produced. Suppose that we were in 1940 and we got like a very energetic particle. What could we invoke to explain them? Well, nowadays, actually, since maybe the 90s, this was very popular. People had these top-down models. Why top-down? Because, well, it starts from top down. They have something exotic, whatever it's weird, you can have on this list. So you'll get one of these weird entities with a given energy whose byproducts of interaction, decay, and so on, produce very energetic particles. And the particles that we detect here at Earth with very, very high energies would be the particles resulting from these other ones. That's why it's top-down. But there is also the more reasonable thing, astrophysically motivated and so on, which is the bottom-up. We start with low-energy particles, and we keep increasing their energy from the bottom up. How do we do that? Well, we can think about invoking some type of interaction or force to do that. Electromagnetic processes or even gravitational processes, and this is not something you hear a lot. It's also not something I'll discuss a lot. I'll just show you one slide on that. Yeah, but these are paradigms, okay? The current paradigm, and I think this is for obvious reasons, it's this one, electromagnetic acceleration. So what we think nowadays is that all these high-energy particles that are produced, they are somehow resulting from some type of electromagnetic acceleration process. I'll not talk too much about this because, well, these top-down models, they predict some other signatures, like as byproducts, and many of them have been excluded, for example, by the non-observation of very energetic photons in this energy range. So this is the integral photon flux in units of per kilometer squared, per steradian, per year. These are the upper limits from several experiments, these markers, and these are the models. You see that, well, of course, they plotted the allowed models, and some models, they are starting to be excluded. These are the last ones alive at the moment, until someone, of course, it's very easy to cook up a model, so you can always tweak your model to just evade the latest constraints, and you keep doing this forever, but it's not nice because you don't learn anything. At some point, I think it's just reasonable to give up on some of these things. But which does not mean that this contribution doesn't exist. It just means that given that the hypothesis of a top-down model is true, we would get a lot of photons that would be related to the cosmic rays, and given the model and these photons, we don't see these photons. Therefore, we can exclude those particular models. But this contribution might be there, subdominant, but might still be there, okay? Okay, now let's go to the bottom-up models, which is the obvious paradigm, a very reasonable thing to do. This one, it's not something that it's very widely mentioned because it requires a lot of fine-tuning. Let me just give to you an example. It's usually the particles within these models, they would be accelerated by some type of gravitational scattering type of thing. So let's suppose we have a rotating black hole, which is a Kerr black hole. For example, this work proposes that this type of black holes can accelerate particles to arbitrarily high energies. How does this work? Let's take a look here. So we have, this is the circle, is the event horizon of a black hole. This black circle inside, this is the singularity of the black hole. So this, if you get inside this white region, that's, you're done. So yeah, you cannot come out. But because this is a rotating black hole, you have this region here called the ergosphere, this gray region. And what happens is the following. Suppose you have two particles with energies E1 and E2. They come into the ergosphere, very close to the event horizon, but not exactly inside the event horizon. And they just bump into each other, exchanging energy. What happens here is that they generate E1 plus E2, go into E3 plus E4. One of these particles fall into the event horizon, and the other one will have gained energy from this interaction and escape the black hole. This is a very logical way to produce high-energy particles as well, because you have two particles with a given energy, and here you can produce, for example, the E4 particle, it will fall down here, and the E3 has an energy larger than E1 plus E2, so you have a net energy gain in the end. A viable mechanism, something very interesting. Yeah, here it's more or less the same type of reasoning. Yeah, but the problem with this type of mechanism is, although it seems logical, the efficiency is not really clear. You need to have all these particles in the ergosphere, and what guarantees that the resulting E3 particle will escape and not also fall? Yeah, so it requires a lot of fine-tuning. This is a tricky model to work. Yeah? Yeah, you have orbits around the black hole with negative potential energy, so effective potential energy. That's the principle. Yeah, you probably did that like in when you were doing like the classical mechanics course, with a central force type of exercise, you have this curve with a negative potential, effective potential. That's what explains how one particle goes inside, carrying more energy. But the net energy gain of the particles that are coming out, it's positive, right? But total energy is conserved, of course. Yeah, but very interesting. Not clear if it's going to work. Next thing, electromagnetic acceleration. This is the paradigm. This is what most people do. Whatever you're doing, gamma rays, neutrinos, and so on. In some sense, electromagnetic acceleration is what's somehow producing a lot, if not all, of the particles that you're studying. This plot that you are seeing, it's a version of the so-called Hillas plot. Many of you might have seen this before. And what we are looking at. You're looking at, in the vertical axis, we have the magnetic field of a given astrophysical object. In the horizontal axis, we have the size of this astrophysical object. And here we have several types of objects that could accelerate cosmic rays or any type of charged particle. So electromagnetic acceleration accelerates particles that are charged. Right? So these are the objects, and therefore you need this magnetic field. What we see is the following. The way to read this plot is the following. If you look here at these diagonal lines, with a given energy, this is, for example, this blue, it's 1 eV, 10 to the 18 electron volts. If you have a particle with 10 to the 18 electron volts, viable candidates have to lie above this line, okay? And the principle underlying this mechanism, this type of plot, is very simple. We use it because it tells us to which energy a particle can be accelerated. Let's understand what's happening. So if we have a given object with a radius, so we have an object, right? This object, it has a given gyro radius or Larmor radius there. It depends on the energy. So this object, this particle will keep being trapped by the magnetic field of a given object, right? It will keep trapped inside. So we'll never detect it. In order to detect it, we want the particle to leave the object. And how does the particle leave? Well, if it's gaining energy, it's gaining a little bit of energy, and eventually, the size of the Larmor radii, or the gyro radius that this particle describes inside the environment, is such that it exceeds the size of the confining region, and the particle escapes. This is a very simple, once again, toy model, right? It captures the main features, but it's a very simple toy model that tells us to which energy, maximum energy, an object can accelerate a particle. If we want the particle to stay trapped a little longer to gain more energy, we would need like a larger magnetic field, for example, or conversely, a smaller radius, this type of thing. So this is the simplest thing to do. So the Hillas criterion says that, it follows a paper from Hillas, 1984, in which the maximum energy, it depends on the magnetic field, the Larmor radius, and a few other factors here. But yeah, bottom line is this. So let's take a look once again at the plot. Either we need to have objects that are very small, like star-sized objects, like magnetars, neutron stars, white dwarfs, like that, or that are very magnetized with very high magnetic fields, or we can have like weaker magnetic fields, like here, but the object has to be big enough to keep confining this particle so that the particle can gain energy until it can escape. This is the way to read this plot. And what we are talking about, it's this electromagnetic acceleration paradigm. We are usually talking about cosmic rays and electrons, right? So how are high-energy particles usually produced? I just told you. Charged particles are produced within the... This is certainly a way that works. The others might work, those other mechanisms that I mentioned before, but let's just talk about this, which is the main one, the main type of thing. Charged particles are accelerated via some type of electromagnetic process taking place in astrophysical objects. But this is true for charged particles, cosmic rays and electrons. So how are neutral particles produced? Through particle interactions. So ultimately, even if you are a gamma ray astronomer, ultimately you have either an electron or a cosmic ray there. If you're doing neutrinos, very likely, like 99.99% of the time, you have a cosmic ray there that produced your neutrino. Okay? So there are several types of interactions, like photohadronic and photonuclear, that produces cosmic neutrinos from cosmic rays, electromagnetic interactions, and so on. There are several types. But now the question is, how can we accelerate these particles to high energy? So we understood one criterion, which is, well, if my object is small enough for a weak magnetic field, it cannot confine the cosmic rays there for very long. Therefore, it cannot explain very high energy cosmic rays. Therefore, we need to come up with a mechanism for particle acceleration. This is what the Fermi mechanism is. I'm sure that many of you have heard about it before, and some of you might even done this derivation at some point, but yeah, I think it's instructive for those of you who haven't to do it quickly. Yeah, so the Fermi acceleration mechanism, it dates back to 1949. Enrico Fermi was the first one to propose a mechanism for the acceleration, electromagnetic acceleration of particles to high energies. And I'll do it here. Okay. Okay, so let's, yeah, I'm going to just outline the derivation of the Fermi acceleration mechanism. There are two types of Fermi acceleration mechanism. I'm going to show, to outline a derivation that works for both of them. So the way this goes is, we are trying to explain particle acceleration. So let's think now of, we have a high energy particle here, right? It's hitting another particle. So this high energy particle, it's moving with an energy, initial energy EI, and then initial momentum PI, right? And this is forming an angle in the lab frame. Let me call this the lab frame. With an angle theta I with respect to this frame that I just drew. So now this particle will come and collide with this one. For those of you who have seen this, I'm presenting another type of derivation, okay? I'm not going to use that cloud thing, at least not for now. I'm going to soon come to that. And then what happens afterwards is that this particle, so this is before, yeah, you understand that. So afterwards, what's going to happen is that this particle is going to escape with a given angle. Theta F with energy EF and momentum PF. I wrote here the lab frame, but there is also this other frame, which is the frame of the particle. So the frame of the particle of this other, not particle, but this, I don't know how to call this. In the original derivation, they call this a cloud, but I don't want to call it a cloud. Let me, yeah. The target frame, okay. So we can have, in the target frame, we are going to have primed quantities, so, right? Yeah, it all depends on which frame we are dealing with. So this is a scattering thing. I'm not talking about the electromagnetic part yet. How do we treat a simple scattering here? Well, the energy in this frame of the target, the primed quantities, it's I forgot to say one important thing, which is that this, the target, maybe I can use this thing here. the target is moving with velocity v. Okay? So I'm just going to do a Lorentz transformation of this initial energy to the frame of the target. So now I'm putting myself here in the place of the target to see what's the energy of that particle in that frame. We have this dot product of the Lorentz transformation. And from here, we get an important thing. I'm going to solve now for EI. And soon you're going to understand why I'm doing this frame change. Okay, this is a useful result. Let's keep it here. Another useful thing to do is the same, but for the final part. So the final energy, and for those of you who might be wondering, so this gamma, it's 1 minus beta squared to the minus 1/2. And beta, it's defined as this velocity here divided by the speed of light. So same thing here, final energy written in terms of the, no, final energy. Yeah. There. Missing a prime, thank you. So now what are we going to do with this? You need to gain energy. That's the whole thing. We want to gain energy now. And what's an energy gain? An energy gain, it's a delta E over E, in which the final energy divided by the initial energy. So an energy gain is that. So we have a final energy minus an initial energy divided by the initial energy. So this number has to be larger than 1 if it's a gain. Right? It makes total sense. And now what do we do? Straightforward, we just plug this into that. Wait. Yeah. Yeah. And there is a -1 here at the end. So I just wrote down those equations here. This is a frame transformation thing. I'm talking about scattering so far. I'm going to make the connection with the electromagnetic part soon. And now, this is the part where this derivation that I'm presenting, it differs from the others because I'm going to do it in a slightly different way from what it's usually done. There are things here that we don't know. Let me just write this in a more convenient form, perhaps, which would be just to clean it up. The convenient form, I think, at least for me, will be this. There is a wrong sign somewhere here. Which one is that? It should be the one here. It's minus, yeah. Okay. So this is a net energy gain. Good. Now comes the part like Fermi. For Fermi, there was he came up with a type 2 mechanism in which he said, okay, here we have one particle entering a magnetized region. So we have a particle coming in here, and then the particle, it will kind of move around here and leave. This, every time the particle is changing direction, you can think of it as a kind of ping pong or a mirror or something like that. The particle moves, it gets hit in the other direction, or if you ever played pinball like crazy, pressing those buttons on the side, that's exactly this. You see that the pinball, it keeps going faster and faster, right? For me, in this original paper, this was a magnetized cloud. These are magnetic scattering centers, right? So it's the typical distance of the characteristic length of the magnetic field. This is why this type of mechanism is considered electromagnetic acceleration. Okay. Yeah. So this is the Fermi second order. It's the one shown in this paper. But this is not the final form. I mean, I didn't tell you anything, and I said that it's second order mechanism. There is no way that you can guess why it's second order based on this equation. What do we do now? Okay, we started considering one particle hitting a target, whatever it is, but it actually hits many targets here, right? It hits many targets before it leaves, therefore we have to do an average. But this average, I mean, how should we average over something that we have one, but we don't know the full distribution? We need to have an intuition of the full distribution. And the intuition of the full distribution, it comes by adding some distribution functions in the end. So what we have to do, ultimately, is calculate delta E over E, which is the average, the net energy gain. And how do we do that? Well, we get that value that we already have. What don't we know here? This beta, everything, the beta and gamma, that's fixed by the construction. We don't know theta I, we don't know theta f prime. Therefore, we need to come up with a function W of theta I and theta f prime. And integrate over these solid angles. Oh, my space here, it's over. Oops. Okay, so what I'm going to do is an average. This is a probability distribution function. We know how to do that. So the probability distribution function is such that if I integrate, actually it's a double integral. If I integrate over the solid angles, that is equals to 1. That's what the probability distribution function is. And this probability distribution function, it's telling us what are the most likely cases for interactions here. So this particle is moving in, the target is moving in one direction. The other particle, it's coming here. Well, if the angles are back, it should not be very important, right? So what are we missing to do this derivation? What we are missing is this W function. That's what we are going to build intuitively. Just to make things simpler, let me define mu as cosine theta I cosine theta f prime. And therefore, I'm rewriting that just for just to keep according to my notation. Delta E. Okay, this is what we want to calculate. This is a probability distribution function, such that if we integrate it, it's 1. Now we need to find this. So let's first assume that omega is independent of that the initial and the final angles, they are not correlated to each other for simplicity. And what do we have to assume here? Well, very important assumption. Let me erase this. So we need this function. How to get that? We assume that the final angle in target frame is isotropic. What does that mean? That means that this nu, which is related to the cosine theta prime f here, well, if I'm the target and I'm moving and these particles are coming to me, I think it's isotropic is a very reasonable assumption. There is no preferred direction in my frame. Especially because if you think also about the cloud in the end, the particles will go all over. Okay. The second, well, if it's isotropic, there is no preferred direction. I don't need to worry too much about this new component. Now, for the initial angle, the average energy gain, it's going to depend, of course, on the... It's going to depend, well, if this particle is moving more in this direction here, backwards, it's not going to hit the target. If it's going here, it's not as efficient, so head-on collisions are preferred. Right? Mathematically, that would be something like a distribution like proportional to 1 minus beta mu, so cosine theta I, okay? This is preferring head-on collisions. That's where we get also the relativistic effects. And therefore, we can get this dw function. We are going to see that here there is no preferred direction. It does nothing. It's a constant. And here there is that term, 1 minus beta mu. I plug this into here, solve the integral, done. That's it. That's the second order Fermi mechanism. And what we get in the end, after the integral, it's four-thirds of beta squared, more or less, on average. Okay, then you might be wondering, why is it second order? It's because there is a 2 here. Well, if there is a second order, there should be a first order, right? But the second order is easier. That's why I started with it. Now, I'm going to use exactly the same type of derivation for the first order. So now, assumptions, let me write that this is firm 2. Now for the firm is first order. For the firm first order, we are going to do exactly the same type of reasoning, so the challenge is just to find this function. And why is the Fermi first order different? Now, this is Fermi 2. So now, for the Fermi first order, Fermi 1. Things are slightly different. This is a stochastic mechanism. Why is it stochastic? Because, well, the particle is moving here, it's spread all over, it's a bit stochastic, as the name says. The Fermi first order, it's also called DSA, diffusive shock acceleration. Shock, you have a shock. And I'm going to tell you what a shock is very soon. Well, a shock is essentially a discontinuity in something, right? You have something moving, it's a shock. So for the Fermi first order, you have a discontinuity. So this is the shock front. And effectively, what's going to happen is that you have a particle somewhere, and the shock is moving. So it's doing this job of this target. And it's going to get to the particle, and the particle will move. It will keep crossing the shock back and forth. This is a ping pong or pinball, and it's going to get energy, gain more energy increasingly. Diffusive shock acceleration. This mechanism here, I'm going to show. So notice the following. In this one, in the frame of the target, the particles would go all over in the end, because it's the notion of this cloud. So you have an isotropic theta prime f. But now we have a shock. If we have a shock moving in this direction and the particle is crossing, in this case, we have a direction, a preferential direction, which is this horizontal axis. And this function, w, it will change. And the function that we are going to get, well, in this case of the shock, of course, the more inclined, the less efficient. The more perpendicular, the more efficient. So there is a cosine dependence. Therefore, if we write this function now, it's going to depend on the cosine of the angle of the particle, which is or cosine theta I, which is mu there. It's the particle crossing back and forth. And also, since the shock is coming here and the shock front is very big, we are not assuming a tiny shock front, there is also that new dependence, because the particle crosses here, then it crosses here. So you understand that this direction here, it's preferential, right? There is a cosine both for the particle and for the shock. Hence, this form. And what we get in the end, it's a delta E over E, which is 4/3 of beta. First order in beta, more than 1, energy net gain. Fermi first order acceleration. There are many gaps here, though. Okay, first thing, this derivation is not the conventional one. This is, this type of average thing, I think it unifies the acceleration mechanism in a better way, but I have not seen it actually I have not seen it anywhere, but it does unify both Fermi mechanisms, so I think it's more pedagogical. So now we have two mechanisms. One is second order, the other is first order, and the difference between them is just the geometry. Just the geometry, there is nothing else different. Okay? In one of them, the frame, it's this frame change that actually leads to the energy gain in the end, if you think about it. That's why I'm doing all this frame change. If I didn't do it, there was no way to get an energy net gain, at least not mathematically. Right, so, okay. Yeah. Oops, sorry. Yeah, I want to compare both mechanisms. So the second order, it's a stochastic process. Right? This is a shock acceleration, so you have particles crossing back and forth the shock front. Assumptions here is, well, the final angle, it's isotropic in the cloud frame, so this contribution, it's proportional. It's a constant, essentially. And here, it favors head-on collisions, whereas on the other side, the fact that the particle keeps crossing the shock front, it leads to this behavior when we do the averaging in the end. Right? So essentially, what I did was a scattering. I calculated what this scattering, what it would look like, and now I'm averaging over different types of geometries. And these different types, they are motivated by astrophysical yeah, they are motivated by astrophysics. So this is a shock, like a supernova exploding. This is just a magnetized region, for example. The energy gain here, it's proportional to beta squared, hence second order. Here, it's proportional to beta, hence first order. And what's going on? I drew it there more or less, but it's this. What's going on? So the particle, yeah, it keeps bouncing back and forth inside the magnetized region many times. And when you average over all possible regions, you get a beta squared energy gain. Whereas in the diffusive shock acceleration, you get a beta factor, so it's much, much more efficient. Yep. Yep. Yeah. No, when it's accelerated, it goes away, but there is a probability that will remain trapped, and we are coming to that. Yeah. Actually, since I'm late, maybe we are not coming to that, so I should maybe answer now. But let me get to the shock part. If I forget, you remind me. So I mentioned shock. Let me explain to you what a shock is. I told you it's a discontinuity. So it's a shock front. You have something that we call upstream. So it's the shock moving, right? We have the upstream, we have the downstream of the shock. We have a density, a pressure, a velocity, and a magnetic field. And where do we find shocks? Well, we find shocks in supernova. We find shocks in pulsar-ring nebulas. Like we have termination shocks, we have AGN jets, GRBs. We've heard about that here already many times. We have also mergers of galaxy clusters, and so on. This set of conditions, Hankin-Hugoniot, it's also called jump conditions. It tells us what happens at this interface. So a shock is an interface problem. What happens when a bunch of things on this side meet a bunch of things on this other side? What happens in this case? Well, we have the density times the velocity. It conserves up and downstreams, and everything else here. And here, for this last equation, we have this pressure term. This is the 5/3 for ideal gases, this gamma C, right? So this changes depending on how you are dealing with it, but for the simplest case, this is 5/3. It's related to the heat capacity of a gas. So just a visualization of what happens in the shock. So, yeah. So we have an electron here. The shock is moving, an electron keeps hitting back and forth here until it goes to the other side. Yeah, I think this also answers Claudio's question. So you have a particle here in the beginning. It kept bouncing back and forth. Let me just play it again. So have an electron, a proton. So the shock is here. So the particle is on the other side of the shock here, the upstream. Yeah, it keeps there, it goes there, but not really. It comes back. So it keeps moving around this interface of discontinuity. And eventually it gains a lot of energy, and there is a probability that it will just escape. It's a non-zero probability that it will escape. And this probability is determined by the shock condition. So the material on one side, the material on the other side, and so on. The temperatures, the magnetic field, that's what determines what happens at both sides of the shock. Here it's a work from 2008 by Spiatkovsky. There is a simulation here. So this is the shock front. This is the interface, the discontinuity. Each one of these lines is a different particle. And this is kind of the Lorentz factor. This is time growing. You see that the particle gets here. So yeah, a lot happened here. Most particles, when they are on one side of the shock, that we call upstream, they go here, they keep moving in now a straight line, not so much. And then here, a lot of things happen, because that medium, that interface, well, it's a discontinuity. So if you ever try to solve an integral of a discontinuous function, like numerically, you see that most methods don't converge anyways, because this is a difficult thing, right? So things keep coming back and forth, one side and the other. And with time, after many, many crossings, the particle will gain energy and it will leave. So there is an associated escape probability, which I don't think I'll have time to do, although it would be nice to show you that this is a power law spectrum, that underlies everything. So yeah, with these we get a spectral index around 2. So I'd like to show you this plot in particular because what we are seeing here is the density row. So on the upstream of the shock and the downstream. And here we have the energy density of the magnetic field. So the magnetic field, you see, this is why it's an electromagnetic type of acceleration. We have the magnetic field here in the interface. This is where action takes place. This is where things really happen. Here we have different densities, right? Because this is the shock. And intuitively, the shock, if you've ever been on a mosh pit in a metal concert, you know what a shock is, probably. There is a bunch of people jumping all over, and then everybody around is trying to move, and then it moves the next layer, and you were on the back, you are probably going to get squeezed if you're close to the interface, which is the wall. And then with the motion of people, that's the velocity. So you can imagine this as the temperature. So the mosh pit, the loudest and the faster the music, the higher the temperature. It's the same thing that's going to happen. And we have a relativistic shock efficiency, usually like a typical value that was gotten in these simulations of 10%. And just for the record, like for shocks, we have around stars also shocks. This has nothing to do with the high energy cosmic rays, but just to build an intuition of what happens in terms of shock. The sun has let's say, a zone of reach, which is related to its shock. And the Voyager spacecraft, it left the solar system. But how do we know it left the solar system? It's quite hard to just look and say, okay, here's the solar system, here it's not. Well, but in this case we can do, because Voyager was still taking data, and you see that at one time, the number of particles being detected per second, it decreased drastically. This is the end of the solar system. This is the end of the shock of the sun. So the end of the solar system, in this case, it's where this sphere of influence of the sun ends. It's a shock. It's the shock interface. Yeah, it's the solar wind, yeah. But the sphere of influence of the solar wind, it's like the shock interface there, right? Yeah, so the front. This is, it is, okay, this is a bit more complicated because it's self-feeding, right? There is constantly a shock. You turn it, yeah. Yeah, do you get it, what I mean? It's because it's kind of self-feeding, so it's always there. There is a sphere of influence. It means that here, there is no sphere of influence, and the sun always keeps, yeah? Yeah, kind of, yeah. Yeah. Exactly. Yeah, it's just two groups of people going against each other. This interface of two groups of, well, in this case, not people, but particles going against each other, it's the sphere of influence of the solar wind. Because there is a characteristic temperature, wind, emission rate of the solar particles that when it meets the other side, it can only win up to a certain distance. Then it can no longer win. This is this sphere of influence, and this is where how we know that the Voyager spacecraft left the solar system. This is actually important for people who do galactic cosmic rays, because you need to consider the effect of the solar wind on the cosmic rays. So this is an important effect as well. Okay, one thing that I'm still unsure. Are there questions so far? Yep. That's a longer, yeah.
Yeah, and here you draw at the random direction.
Good, yeah.
Should I repeat?
There are, yeah.
Okay. So in textbooks, normally they draw a magnetic mirror, so the direction of the particle that is exiting is like in the has opposite momentum.
Yeah.
Here you draw, well, not it.
Then you get an 8/3.
Huh?
Then you get 8/3 of beta squared instead of 4/3 of beta squared because it's a mirror, so you have this symmetry. This is the Longueur derivation.
Yeah.
There are both types of derivation. It depends on whether you average over the pitch angle. This is what I did.
Yes. So in my question would be if there's a physical interpretation for such magnetic mirror, because it's looking like.
It's just the geometry of the problem, right? You were answering different questions. In the end, physically speaking, you'd get kind of the same thing, but disconsidering half of the like particles living on, you would consider only one side, not the other, on average. Yeah, that's why you get this factor 2.
Okay.
Yeah.
All right.
Here, I'm averaging over pitch angle. So in my case, there are particles living backwards, and they don't come. When I do my average, I get the 4/3. In this Longueur derivation, for example, the magnetic mirror, you'd get an 8/3. Exactly because you disconsider. You don't do this average over 4 pi. You just do a 2 pi average.
And both are right.
Yeah, as long as you know what you're doing, yeah. This derivation here, in particular, this construction, this is the way that I think unifies both. Yeah. Are there more questions? Nope. Okay. Thank you. Yeah. So, I was wondering whether I should continue or maybe I should show that we get a power law out of this. What do you prefer? Power law? Huh? Yeah? So should I show that we get a power law out of this? Raise your hands. Oh, this is very half and half. Okay, I'll try to do both. I'll sketch the derivation. Okay. Yeah, I'll sketch the derivation before we move on. Here. So the whole idea. Let me show this for the second. Well, I would need to show for both, but the derivations are similar. For Fermi second order. Okay. So power law. Okay. So for the second order, we want to show the spectrum, right? So we start with something very simple. We count the number n of particles per time. Well, that's what we want to do, more or less, at least for starters. This we can write. Right? And all of these, it's okay, so essentially, this is an intermediate step. Look here and here. The derivative, the time derivative of the number of particles, with many, many assumptions, rule of thumb, again, toy models just to make this understandable. We have the number of particles escaping with a characteristic time scale, tau scape. Sorry, yeah. And this is an intermediate step that I'm going to use now. So dE dt dE dt in this case on this side. So this on this side here, I'm going to tell I'm going to describe the acceleration process, right? How the number of particles change with energy and with time. So the acceleration, such that dE dt, if I'm assuming in the very simple case, which is not really correct, but it's a good starting point, I'm assuming that the energy gain does not really depend too much on the energy. That's a good approximation if you think like that beta is relativistic, so it approaches 1, and it's going to be always very close to 1, so that the energy gain is going to be, it's going to be approximately constant. But once again, these acceleration mechanisms, they don't always work. In particular, the second order, this is a non-relativistic case, okay? So beta cannot be 1. But yeah, so let's just assume that I can do this. So that I can say that my energy change, the dt, it's the energy of the particle by a characteristic acceleration time as opposed to the escaping time scale. And I'm going to plug that in. I'm also going to assume that tau escape and tau acceleration don't really depend on time. Well, yeah, this is a sensible approximation, actually, at least for this. So if I just solve this equation now, yeah, I think we can easily do that now. We get this differential equation, right? Okay, since I want to do both, I will just skip the steps, the intermediate steps, and jump to the end. This is proportional to. So we get this where. So this is what we get in the end by solving this equation. We get that the number of particles as a function of the energy goes with e to the minus alpha plus 1, where alpha takes these two time scales, the escape time scale and the acceleration time scale together. Right? Because, well, of course, it has to do with how fast, which one wins, the acceleration or the escape. So alpha, in this case, it's going to be going to be 1 plus 1 over tau acceleration plus 1 over tau escape. And from here, okay, this is the result. The usual form that we work with when we talk about power loss, we say that this is true. When we talk about power loss. So the Fermi mechanism, this is the second order. There is a very similar derivation for the first order. Not very similar, but yeah, there is a derivation for the first order. Also easy, which I'm not going to do. But here we can already see that the second order leads to a power law. And we all work with power laws. The cosmic ray spectrum that we saw in the beginning, there are some breaks, but it's a power law, roughly speaking. There are many power laws. Important feature here, e to the minus alpha. Typically, alpha here for the second order mechanism, it's order 2, e to the minus 2. So if you're doing like, for example, gamma rays, and many people that are doing gamma rays assume, okay, we have some type of mechanism, acceleration mechanism, e to the minus 2 type, like a power law, and this comes from the production of the cosmic ray production. So if it's a hadronic model, or if you're doing neutrinos, same thing. So you get power loss out of Fermi acceleration, or out of the Fermi acceleration mechanism. For the first order, I won't have time to do that, but now it's just to count the number of times the particle crossed back and forth the interface, the shock front. If you do that and you assume what Claudio asked about the probability of escaping, there is a probability of escaping time. That's what drives the spectral index. Yep. Maybe, yeah. Okay, I didn't want to open it. Yeah. So we have 1 over tau. Ah, yeah. Sorry, yeah. It's that, or is this right? Can you think faster than me? Is this correct or not? Yeah, you just have to solve this. Maybe I'm mistaken. Yeah, but you're completely right. Alpha is unitless because it's a spectral index. It makes no sense to be different. Yeah, I think there is 1 plus, but I'm not sure. I will check at the end. Where was I? I'm lost, okay. So yeah, I was saying that this is how we get the power loss. Fermi first order. Fermi first order, we count the number of crossings. There is a probability of the particle escaping and the probability of the particle to be trapped in that shock front. And if you count that, you get a very similar type of expression with like an alpha plus 1. And again, also for the first order, you get a very similar spectral index for typical cases, like order 2. Right? Sometimes, like here, you can have like a 2.2, sometimes 1.9, but it doesn't change too much. It's always, in this case, in this type of mechanism, for the typical astrophysical situations, order 2. What are the exceptions? You can have this diffusive shock acceleration, for example, when you have magnetic reconnection, in which magnetic field lines, they just reconnect. And you can easily see that if you have magnetic field lines connecting and reconnecting, you can easily see interfaces and discontinuities for like shock type things. And then you can get spectrum alpha 1 point something or so. Okay, since I have 10 minutes, are there questions so far? Yep. No. Exiting. Yeah. Well, it depends. It depends how you see it, right? When I say that, in this derivation, at the end, we are counting the particles that are exiting. So, but I don't think it matters for the second order, because the equation will be the same at all times. I mean, yeah. It matters a lot for the first order. Actually, this is a mistake that I always make. That's why I prefer to open the calculation for the second one, because there is always 1 minus the probability of remaining trapped or escaping, and I always mess them up when I do this. Okay, so now what I want to talk about before, like in this last 5 minutes or so, it's about the requirements for acceleration, for cosmic ray acceleration. And if you see so far, the fact that the cosmic rays are of high energy, it doesn't matter much, except for the fact that we use air shower techniques to study them. So what are the requirements for acceleration? One of them we have already discussed, which is that geometrical constraint, like the Hillas criterion. There is another one, that the energy, oops. Okay, so we have acceleration, and we have energy losses plus interactions. So we have acceleration, so this is good. So there is a net energy gain, and the acceleration is exceeding by far the energy losses and the interactions, so the particles are having a net energy gain. Because everything that I described here, of course, this medium here, it has other things. And the interactions can occur, these particles can interact. It's much more messy than we are actually showing. We also have this type of curve here, in which the acceleration does not always exceed the energy losses or interactions, such that they kill the particles. So the particles cannot be accelerated to very high energies. They would escape before. This is what this is showing. So effectively, this condition tells us that there is an interplay between acceleration and energy losses and interactions. Of course, it depends on the type of particles, like leptonics, if you have electrons, or hadronic scenarios, if we have protons, that determines the interactions and energy losses that we have to deal with. But yeah, this is a very simple cartoon of what's going on. The other condition, the other constraint is the geometrical constraint, this Hillas criterion. We've seen this plot before. Once again, we want to confine particles until a certain energy Emax, and then the Larmor radius, or the gyro radius of this particle, will be larger than the size of the object, and it will be able to escape. Very simple condition. There is a third condition related to the energy budget. So essentially, there has to be enough power in a given astrophysical object for acceleration. Here we have UB, which is the density of the magnetic field in the region. RO, it's the radius of the object, the typical size. We have the beta of the particle, and so on. And then we can just plug, this is a luminosity, so energy per time. We can just plug the Hillas condition that we've seen in the previous slide, this one. We can plug it here, somehow rework things. So we need a minimum energy requirement for, depending on the magnetic field of that region, to ensure the luminosity that we observe. And those three things that I mentioned so far, the geometrical constraint, this energy budget requirement, and that the net energy gain, in which the acceleration, so the energy gain due to the acceleration has to exceed the energy losses due to interactions, those are what I call the basic, like the real physical fundamental requirements. Some people like to add other a posteriori requirements. So we have, like in this plot here, for example, we have several types of astrophysical objects. We have flat spectrum radio quasars, FSRQs. We have BL-LAC type objects, galaxy clusters, and so on. And there is what I call an a posteriori constraint. So after you detect, you say, okay, I can only detect particles that obey to these conditions, but they are a posteriori because they are after the detection. So they are kind of biased. They are not fundamental. So in this case, you need a given luminosity. So your source has to be bright enough, and you have to have enough density of the sources to ensure that the number of particles that we get here at Earth, it's enough. So you see the cosmic ray spectrum. We've seen that many times today. So we need that each source, we require that each source emits a given amount of energy per time, and we need to have a given number of sources within a given volume to ensure that we observe enough events. Otherwise, it's not a good source candidate, right? But this is an a posteriori condition, because exactly for that reason. Because, well, this is not a good candidate because you would need to have a given number of sources to explain things here. It has nothing to do with the the basic things at the source. It has to do more with higher level things, observational. Okay. And of course, this also depends a bit on the magnetic field and so on, because if you have a magnetic field, even if you have enough density and luminous enough sources in between, the magnetic fields, as we're going to see tomorrow, they might just kick off all the particles and they might never reach Earth, not because the sources are not good candidates, but just because the magnetic field would kill them or make them not arrive at Earth. This is why it's a posteriori requirement. Okay, so maybe I should stop. That one I can cover tomorrow. Anyways, that was my transition slide. I have 3 more. Are there questions? I think this is a good point to know if you have questions. Yeah. Too much or good?
I guess everything was crystal clear.
I hope so.
Okay.
Okay, good.
So I guess we go for lunch, huh?
Yeah.
All right.
I'm also hungry, so.